Welcome to The Explainer. Okay, I am absolutely thrilled for today's session because we are unpacking the ultimate insider's guide to maximizing your marks on literally one of the trickiest topics in the Cambridge AS and A-level computer science syllabus. We're zeroing in on paper 9618, and we are going to completely master the role and function of a router in a network. Now, let's be honest, network questions can feel a bit like navigating a minefield, right? You think you know the material inside and out, you write a solid paragraph about packets and IP addresses, and then the mark scheme comes out, and you're just left wondering where it all went wrong. Well, today we're going to bridge that gap. We're looking directly at exactly what the examiners are searching for, which is going to totally transform the way you approach these questions. So let's dive into this. Why do perfectly capable, smart students lose easy marks on router functions? I mean, you study the OSI model, you know what a router is, so what gives? Well, a huge part of it comes down to interpreting complex data structures, and, quite frequently, some really tricky binary representations. These often trap unprepared students. When you get a question asking you to determine a network address using a subnet mask, it's not just about knowing that a router directs traffic, it's about actually applying bitwise AND logic. It's about precision. Examiners note time and time again that students just kind of panic at the sight of complex data or binary scenarios in routing questions, and they end up leaving super easy marks on the table.
Here's our algorithmic sequence for today. We'll hit the networking mark trap, core academic principles, the procedural execution framework, evaluative thinking and analysis, and finally, top examiner pitfalls.
All right, let's kick things off with part 1, the networking mark trap.
The stakes in the 9618 exam are super high, and network routing is a core pillar of it. But even the absolute best candidates drop points here. Why? Because there is a massive, massive difference between understanding a concept in isolation and actually applying it to a dynamic network scenario. There's a brilliant observation from a senior examiner's report that points out how the classic mistake is providing generic answers that aren't specific to the question context. You always have to link every point to the given scenario. Honestly, if you take away just one thing today, let it be this. Memorization without scenario application is a guaranteed way to lose marks. If the prop describes a router in, say, a small retail store network, and you just start giving generic definitions of a core internet backbone router without ever mentioning the retail store, its point-of-sale systems, or its specific subnets, the examiner literally cannot give you full credit. You absolutely have to anchor your knowledge to the reality of the prompt.
Moving right along to Section 2, Core Academic Principles.
This right here is the foundational architecture examiners expect to see when they're handing out those top-tier marks. They aren't just looking for you to drop some buzzwords. They are looking for a very specific type of academic rigor. Basically, examiners are looking for analytical depth over superficial breadth. Analytical depth involves logical reasoning and cross-topic connections. Superficial breadth, on the other hand, is just throwing a bunch of generic facts at the page and hoping something sticks, which usually completely misses the context. The assessment framework explicitly prioritizes that analytical depth. If you write 5 generic bullet points about what a router does, you're just demonstrating superficial breadth. But if you explain how a router processes an incoming packet's IP address, logically determines the next hop using its routing table, and then you link that back to the specific scenario provided, boom! Now you are demonstrating analytical depth. To actually achieve that depth, you need to lean on 3 core principles. First up, evidence-based reasoning. Don't just claim that a path is faster. Prove it. Reference the hop count or the bandwidth mentioned in the text. Second, precise definitions. Please don't call a packet a message. Use the correct professional terminology. And third, and honestly, this is the secret sauce, integration with other syllabus areas. Principal examiner reports constantly highlight the candidates who make cross-topic connections achieve significantly higher marks. So if you're talking about a router, can you connect its function to data security, like packet filtering? Can you connect routing tables to data structures? Showing that holistic understanding of the entire computer science syllabus is exactly how you impress an examiner.
Up next is Section 3, the Procedural Execution Framework.
So, how do we actually pull this off in the exam hall when the clock is ticking down? Think of this as your bulletproof problem-solving algorithm. You wouldn't write code without a plan, right? Well, you shouldn't write an exam answer without one either. The absolute crucial point here is understanding the method mark strategy. Examiners actively want to reward how you think, not just the final result you spit out. If a question asks you to calculate a network address using a router's subnet mask and you make some tiny little arithmetic error in the final binary conversion, you can actually still get almost all the marks. But, and this is a big but, you only get those marks if you show your process clearly. If you just write down the wrong final answer, you get a 0. But if you show the bitwise and alignment step by step, the examiner sees you understand the underlying concept perfectly, and they'll award you those method marks.
To make sure you nail this every time, here is your standardized 5-step sequence. Step 1. Deconstruct the question. What exactly is the command word? Are they asking you to explain, describe, or calculate? Step 2. Extract relevant data. Pull out the IP addresses, the network constraints, the specific details of the scenario. Step 3. Select your analytical framework. Are we using routing protocols, binary logic, or security principles here? Step 4. Execute with clear notation. Write out your working logically so it's easy to follow. And finally, Step 5. Present with correct terminology. Following this pipeline practically ensures you don't miss a single available mark. Let's jump into Section 4, Evaluative Thinking and Analysis.
Now we are entering the masterclass phase. This is what separates standard passing grades from top-tier A-star academic excellence. Once you have the basics down, how do you show the examiner that you truly grasp the real-world complexity of network systems? By analyzing trade-offs. When you're evaluating a router's algorithm for finding the shortest path, something like Dijkstra's algorithm, you need to consider both time complexity and space complexity. Think about it. How much memory does that routing table take up? How long does it actually take to update when a link suddenly goes down? What are the weird edge cases? By acknowledging limitations, like the processing overhead of dynamic routing protocols compared to the simple rigidity of static routing, you prove incredibly deep evaluative thinking. You show them you understand how these choices directly impact real-world network performance.
In practice, this translates into what we call the deconstruct, solve, and evaluate triad. It's a fantastic mental model. First, deconstruct. Identify the given information and break the whole problem into logical steps. Second, solve. Systematically apply your knowledge, showing crystal clear working. And finally, evaluate. Check for reasonableness. Make justified recommendations based on the evidence. If a router is dropping packets, analyze why. Based on the data they gave you, solve the immediate routing loop, and then evaluate the long-term fix. This triad forces you to be thorough, and examiners love thorough.
And finally, Section 5, Top Examiner Pitfalls.
Okay, listen up, because we have reached our final section, and it is arguably the most important one to internalize before you do your next past paper practice. Consider this a massive examiner alert. The principal examiner reports are practically begging students to stop making these next 3 recurring mistakes. If you can just avoid these, you are already so far ahead of the curve.
Let's look at how these errors cascade into real point losses. Pitfall number 1, forgetting overflow and edge cases. In network contexts, what actually happens when a time to live, or TTL, value hits 0? The packet is dropped, right? But so many students just forget to mention this edge case. Pitfall number 2, ignoring boundary conditions. What happens at the absolute physical or logical limits of the network segment? And pitfall number 3, the biggest one we've been harping on today, failing to anchor answers to the specific context. Remember, if you ignore the boundary conditions of the specific network scenario they gave you, your answer becomes generic, and your marks just evaporate.
So, let's bring it all together. We've covered the mark trap, the core principles, the execution framework, evaluative analysis, and those sneaky examiner pitfalls. Just think about the key terms we've discussed today: context, analytical depth, method marks, evaluative thinking, edge cases. Mastering these doesn't just help you ace the 9618 exam, it fundamentally changes how you see the digital world around you. Next time you send a simple text message, I want you to ask yourself, how many edge cases, subnet masking calculations, and boundary conditions did a router just evaluate in a fraction of a millisecond to get that message to its destination? It's pretty mind-blowing when you really think about it. Keep practicing, stay structured, and keep learning.